Hi everybody, welcome to Turn It Up to a Million, ingesting millions of metrics with Thanos Receive. I hope that everyone's doing well at home, and I'm happy to be here with you. So, I originally proposed this talk because I'm excited to share some of the work that we've been doing inside of Red Hat on the observability team, and also inside of the Thanos project, around ingesting large amounts of time series in a horizontally scalable way. My hope is that at the end of this talk, you'll come away with some concrete ideas around how to build and also deploy a scalable metrics ingestion stack. So, who am I and why am I talking about this? My name is Servén Marín. I'm Spanish. I'm a twin and I love penguins. And I'm also a principal software engineer at Red Hat, where I work on the observability platform team, where we primarily work on building distributed systems for monitoring OpenShift. I'm lucky that at work I get to contribute a lot to open source projects, and I get to work as a maintainer of Thanos, the Prometheus operator, and a bunch of other things. And you can find me on GitHub as @squat. Okay, so this talk assumes some familiarity with Thanos, so I recommend that you take a look at the talk that my fellow Thanos maintainers are giving at this year's KubeCon called Intro to Thanos. We'll also talk a bit about it right now. So, the goal of the Thanos project is to provide a global query view of all of our data, to be compatible 100% with Prometheus, to provide long-term retention so that we can query data from months or even years ago, and also to provide compaction and downsampling so that we can speed up our queries. Thanos does this by providing a set of components that we can compose into custom-built distributed monitoring stacks that suit our needs for different scenarios. A really common deployment pattern for Thanos looks like this. We have one central monitoring cluster with a Thanos querier and maybe a Grafana next to it. And then we have a bunch of different clusters or environments with Prometheus servers that we want to query. So we want to, from one single location, query the data from all these different Prometheus servers. When we go ahead and type a query into the Thanos UI, Thanos pulls the data that it needs from the Prometheus servers by making a gRPC request to the Thanos sidecars in each cluster, and the Thanos sidecar in turn proxies that request to the Prometheus API. All right, so far so good. But what happens if we don't have ingress access to the clusters that we want to query? For example, what if the clusters are owned by customers and they want to share some metrics with us, but they don't want to expose all of their data to the internet? Or what happens if the customers want to share some data with us, but not all the metrics? One option that we have in this case would be to switch from a pull-based model to a push-based approach. It turns out that Prometheus has an API exactly for this use case. It's called the Prometheus Remote Write API. And the implementation is really nice. So when Prometheus is configured to remote write to an endpoint, it's essentially tailing the write-ahead log for the database and sending all of the time series to this remote endpoint. The API has built-in retry logic, request batching and backoffs, and a lot of configurable features that make it really good for replicating data. So the Thanos receiver essentially answers the question of how can we build a Thanos component to accept metrics sent over the Prometheus Remote Write API. This component should be able to ingest metrics that are sent from lots of clients into one local TSDB. So far so good, but imagine what happens when instead of having 2 or 3 or 4 or just a few clients, we go to having an arbitrary amount of clients. So one single component ingesting metrics from thousands of clients is going to eventually break. We need a way to make this component scalable, and that's exactly what this talk is about. Okay, so how do we make the Thanos receiver scale? The approach that we took was to design the receiver as a hash ring of many replicas collaborating to ingest data together. So when Prometheus remote writes data into the hash ring, the request gets load balanced and initially lands on one of the replicas. This replica hashes the received time series and their labels, and it finds the corresponding replica that should handle this request, and it forwards the request to it. So this internal forwarding of requests is what allows us to distribute load equally across all of the replicas, and more importantly, it also allows us to scale the ingestion stack horizontally. The way that we configure the Thanos receiver allows us to place different replicas into distinct hash rings, where each hash ring can correspond to some number of tenants, where, for example, a tenant might be a general purpose telemetry system or maybe a company-wide metrics ingestion service. If we know that one of the hash rings has to serve a tenant that has a lot of clients and ingest a lot of data, then we can scale that hash ring independently. For example, hash ring B might have to serve thousands of clients and needs to have a bigger hash ring with beefier machines. We can accommodate that. On the other hand, if we know that hash ring C only has to serve a few different tenants that are sending very few metrics, then we can scale that hash ring down. But what happens now if one of the replicas is experiencing problems for any reason? Maybe we're rolling out a new version or we're adding more memory to it. Whenever this replica is down, the hash ring has an entire set of hashes, so an entire set of time series and labels that it can no longer forward anywhere. So this means that the hash ring is scalable, but it's not highly available. We solve this inside of Thanos by providing the option for a kind of dynamo-style replication. That means that, for example, if we choose to replicate our data always 3 times, when we receive a request, the initial replica will forward this request to 3 different nodes in the hash ring. And as long as 2 of the nodes respond with, yes, I was able to write this data, then we return back to the client a 200 and we say, this was written successfully into our TSDB. This now allows us to have both a scalable and a highly available ingestion system. This replication scheme means that we can tolerate having one node down at any given time. And that means that we can perform a rolling upgrade of our hash ring whenever we need to without having any loss of ingestion capacity. If we want to tolerate having more nodes down at any given time, all we have to do is increase the replication factor. So for example, if we change the replication factor from 3 to 5 replicas, then we can tolerate having 2 nodes down at any given time. Now that we've designed our Thanos receiver to be both scalable and highly available, we're able to ingest data from thousands of clients into our TSDB. But since we're ingesting so much data into our TSDB, storage is likely going to become an issue on these nodes. We're going to be creating so many TSDB blocks with so many samples and time series that it's going to occupy a lot of space. So storage is going to become a bottleneck. The way that we solve this inside of Thanos is by uploading all completed TSDB blocks into object storage. Object storage is cheap and essentially infinitely scalable, so we can upload all the data we want there. We later make this data queryable by using a component called the Thanos Store or the Thanos Store Gateway. This essentially exposes the same gRPC API for querying data, except instead of reading data from disk or from a local TSDB, is reading it from object storage. Until now, we've seen the purpose that the Thanos Receive component has inside of the Thanos project. And we've also seen from a high level how its hashing design allows us to run it as a scalable and highly available metrics ingestion system. But how do we actually run such a system, and how do we automate it so that it scales horizontally in a platform like Kubernetes? Let's take a look at the details. We mentioned earlier that the Thanos Receive component can be configured into hash rings. Today, this configuration works by using a JSON file to explicitly map the addresses of the different replicas to distinct hash rings. Unfortunately, JSON is not a very human-friendly language, and we definitely don't want to have to write JSON by hand every single time that we need to scale our hash ring up or down. However, Thanos needs this configuration file so that the replicas can discover each other, because Thanos doesn't know anything about Kubernetes or any other cloud or container orchestration system. In fact, this limitation is intentional and actually allows us to keep the Thanos project simple and focused because we don't have to put any non-metrics domain logic in the project. But it also means that we have to lean on other tools to automate configuring our hash rings when Thanos is deployed on such a platform. Fortunately, we have an effective pattern for solving these types of problems in the Kubernetes community, namely controllers and operators. At Red Hat, we've written a small project called the Thanos Receive Controller for the sole purpose of automating the configuration of our hash rings. This Kubernetes controller works by watching all of the stateful sets that match a specific label selector. Whenever the replica count for one of these stateful sets containing Thanos receivers changes, the controller regenerates the hash ring configuration JSON file and updates a config map holding it. The Thanos Receive replicas in turn watch the file system for changes to their configuration. So when the kubelet updates the volume mount for the configuration file, the Thanos Receive replicas reload and update their in-process representation of the hash rings to reflect the new state of the world. With this in mind, let's consider the simplest possible deployment of a Thanos Receive hash ring that's automated on Kubernetes. The deployment would include one Thanos Receive controller replica managing the configuration for one single Thanos Receive hash ring that contains only one replica. So admittedly, this setup might not seem like very much, but it's actually foundational for any more complicated and more capable setups that we'll deploy in the future. It's also true that this stack probably won't handle very much load, but with one single invocation of a kubectl scale command, we can take this single replica hash ring to 3 or 5 or 20 replicas and really handle as much load as we want to. Now let's try to do exactly this in a quick demo. Let's deploy this super simple automated Thanos Receive hash ring onto a Kubernetes cluster. We'll then run one process next to this that produces metrics in the remote write API format and sends them to the hash ring for ingestion. By the way, all of the commands, instructions, and manifests that I'm using in these demos for my talk can be found on my GitHub in a repo called kubeconu 2020. What we're going to do is deploy a Thanos Receive hash ring and also a Thanos Receive controller along with it to configure the hash ring. So let's begin by creating the namespace for our cluster. This is going to be the Thanos namespace. And now we're going to create all of the manifests that we have in the directory for our first demo. All right, great. Now let's take a look at what manifests we actually deployed. We have a bunch of manifests corresponding to the Thanos Receive controller itself, and then some manifests corresponding at the bottom to the Thanos Receive hash ring for our default hash ring. Here we have a staple set with one single replica. So when we take a look at the pods, we have one single Thanos Receive pod in the default hash ring, and we also have the Thanos Receive controller pod. Let's take a look at the configuration that the Thanos Receive controller generated for us. You can see that from the one pod that we had in our staple set, we generated one endpoint for our hash ring. Perfect. Now let's run a second process in another terminal where we're actually going to be generating some metrics to ingest in the hash ring. Here we're going to be using a binary that we wrote at Red Hat called up that simply sends one single metric, an up metric, to an endpoint that you specify via the remote write API. And now let's scale up our hash ring from one replica to 3 replicas. Let's take a look at the pods. And it seems like everything rolled out perfectly. And during this rollout process, we didn't drop any remote write requests, it seems like. So now let's look at the hash ring configuration that was generated by the Receive controller. And as you can see, now that we have 3 replicas, the Receive controller updated our hash ring configuration, and our endpoints array now has 3 endpoints in it. Exactly what we expected. And now when we quit the up binary, we can take a look at some statistics, and we can find that we sent 100 remote write requests. We sent 1 request per second. We just saw how we were able to effortlessly deploy a hash ring onto Kubernetes, and then with a single command, scale that hash ring up, for example, to handle increased traffic. I think that these kind of easy wins are oftentimes underrated. In fact, inside of Red Hat, we're running essentially exactly this same stack as part of the OpenShift monitoring platform. One of the services that we run is a Thanos Receive hash ring with 6 replicas that ingest metrics from on the order of 10,000 OpenShift clusters. These OpenShift clusters report data to this platform regularly throughout the day so that we can identify and alert if these clusters are experiencing any issues, for example, something wrong with the control plane or something going on with the nodes. Of course, since we're the observability team, we closely monitor all of the services that we run. So I was pretty easily able to get some statistics around the amount of data that we're ingesting. As of late July, when I recorded this talk, we're regularly handling around 10 million active time series, and we're ingesting on the order of 30,000 samples per second. So that's actually pretty low frequency data for the amount of time series that we have. And that's because each of the clusters that reports data to our platform only sends data about once every 5 minutes for a pretty limited set of time series. In the case of this OpenShift monitoring production service that we're running, we're able to pretty accurately estimate the load that we're going to have this week, next week, in a month, or in a quarter. And this means that we're able to plan the capacity effectively for the size of our ingestion hash ring appropriately. This is possible because we have a good idea of how many OpenShift clusters there's going to be in the wild, and we know exactly which time series these clusters will be sending and how often. But nevertheless, every few months, we need to resize our cluster, resize the hash ring in order to accommodate the increased load, which means that we have unnecessary toil for our engineers. And this problem is even more pronounced for workloads that are spikier in nature than ours are. So imagine that the amount of time series and samples that a hash ring needs to ingest are varying wildly from peak to trough. This kind of volatility means that it's going to be really difficult to appropriately size an ingestion service. So without good automation, in these cases, the best option that we have is to over-provision the service so that it's able to handle the highest peaks. But obviously this has the downside of causing the service to be really underutilized in times of low traffic. So we're going to be wasting both resources, and that means we're going to be wasting money as well. In the case of the Thanos Receive Controller, we can use the horizontal Pod Autoscaler to scale the hash ring up when the hash ring is swamped and using too much CPU. And then we can use the Thanos Receive Controller to automatically regenerate the configuration for this hash ring, and then have everything working for us just out of the box. Let's try running this exact configuration of an auto-scaling Thanos Receive hash ring in a new demo. This is going to look a lot like the first demo where we had the Thanos Receive Controller generating the configuration for a Thanos Receive hash ring, but with the added change that the hash ring is going to scale automatically when we're increasing the load on it using the horizontal Pod Autoscaler. The horizontal Pod Autoscaler in turn is going to depend on the availability of the resource metrics API in the cluster. So in our case, we're going to be using the Kubernetes metrics server to provide that. And another thing we're going to be doing here is we're going to be generating a lot more load than before. We'll be sending hundreds of thousands of time series that are going to be changing every few seconds to really stretch this hash ring a little bit more to its limit and see how it stabilizes and how it performs. All right, let's begin again by creating the Thanos namespace. And then we're going to deploy all of the resources in the directory for our second demo. And you can see that a lot of these look like before, but let's take a look at the few things that are different. So namely, let's look at the Thanos Receive staple set. And one of the things we can see here is that we're deploying a new sidecar inside of the Thanos Receive pod. This is a sidecar called config map to disk, and the purpose of this is to automatically synchronize the config map that's in the API to a file on disk, instead of avoiding the long resync loop that it might take when the kubelet has to update the volume mount. This sometimes, when a config map changes in the API, it can take a long time for it to be reflected on disk. So here, we're just trying to have the hashrings.json configuration file update a little bit faster. The next thing that's different in this demo is that we're deploying a horizontal Pod Autoscaler resource. And here we're setting the minimum replica count to 5 replicas. This means that we're always going to have at least some ingestion capacity in our hash ring, and that means at a minimum 5 replicas. The other thing that's notable here is that we're scaling based on the average CPU utilization of the hash ring. So when the average utilization of all the pods in the hash ring reaches 50% of the CPU that they requested, then we scale up. Let's take a look at all the pods that we have, and if everything rolled out correctly, we can also see that the configuration generated by the Thanos Receive Controller should be there. This looks good, so let's take a look at the pods. All right, this looks good. So let's run in a second terminal a process that's just watching the horizontal Pod Autoscaling resource so we can see the decisions that it's going to be making in real time. And now in one last terminal, we'll run a process to generate load against our hash ring. In this case, we're going to be using Freshtrax's Avalanche project, which is a binary that generates remote write requests against some endpoint that you choose. One thing to note here is that we're using a fork that I made that's very tellingly called log errors. So the original binary, when it reaches 20 errors, it just exits. And in this case, we want to avoid exiting and just keep logging errors. So that should serve a little bit as an indication of where this demo is going to go. Another thing to note here is that we're going to be deploying 1,000 metrics, each with 100 different time series. Pretty soon, the horizontal Pod Autoscaler scaled the hash ring up to 7 nodes. And when this occurred, the process generating the load against our hash ring started logging a lot of errors. This means that our hash ring is in some kind of unstable state. Soon after that, the Pod Autoscaler scales once again the hash ring up to the next 10 minutes of this. The next 10 minutes of this demo are pretty uneventful. The hash ring is super stable at 9 pods, and we're not generating any errors. So let's fast forward a little bit. In the top screen, we're now running kubectl top to see in real time how much CPU and memory each of the Thanos Receive pods is using. One thing that we can see is that whenever the process that generates load changes the time series that it's sending, the characteristics of the CPU utilization change as well. The reason for this is because every single time that we change the time series that we're sending, we also change which final Thanos Receive replicas these hash rings end up on. So it means that the characteristics of which pods receive how many metrics and which pods have to forward metrics to which other pods changes. So we might sometimes have a very smooth distribution of metrics, and other times we might have very lumpy distribution of metrics where a lot of time series get clumped up on one node. Now at around 23 minutes, the avalanche process reconfigures itself, and it seems that the distribution of time series in this case is causing a really uneven distribution of metrics and increasing the CPU utilization of the hash ring. This is causing the hash ring to become unstable and is going to require a scaling event. Now when this hash ring scales up, we further destabilize the hash ring because some of the nodes are unavailable for some amount of time, which causes more errors in the hash ring, causing more CPU utilization, etc., etc. Now when this occurs, we end up scaling the cluster up all the way to 20 replicas, which is actually the max that we set on our horizontal pod autoscaler resource. And at this point, the pods will eventually stabilize, and the CPU utilization, we can expect it to drop. Around the 31-minute mark, the hash ring finally stabilizes, and the CPU utilization will begin to drop. Now, the CPU utilization will keep dropping so much that the horizontal pod autoscaler elects to scale the hash ring all the way down to 12 replicas, where the hash ring seems to be pretty stable, and at some point we just quit the process because this has given us already a lot to think about. Compared to the first exercise where everything was rainbows, this demo didn't quite go as smoothly as we would have hoped. Yes, we did finally reach some stable state where the hash ring was able to ingest all of the data that we were throwing at it, but along the way, every time that we had a scaling event, we had inconsistent states where we were dropping requests and we couldn't ingest the data that we were being requested to do. Even though these experiments don't go 100% smoothly, they provide a super good insight that helps us understand the systems that we're designing. In the case of the Thanos receiver, we can begin to ask questions like, why is this hash ring behaving so erratically, or is it so unstable? One of the ways we can imagine the system is that we can describe it as being an unstable equilibrium. This would be, for example, if we're balancing a really tall and slim item vertically, or if we have some kind of pebble that lands in a local minima. Any small disturbance might nudge this thing out of its equilibrium state and into some totally chaotic state. In fact, this chaotic state that we're landing in is some kind of positive feedback, where we're generating more instability the more unstable that we become. To help understand the instability of the system, let's think about some of the instances where we had long spans of time with a lot of errors. So one of the notable instances was when the horizontal pod autoscaler scaled the hash ring up to 20 pods. What was occurring was that there were only 15 pods in the system, but the stateful set resource had 20 replicas in the spec. The reason for this was that the stateful set controller only created 15 pods in the cluster because we only wanted to have one unready pod at a time. The end result is that there was a mismatch between the amount of replicas that we had in the endpoints configuration file for our hash ring and the amount of replicas that were actually available. This means that we had tons of requests that were destined to endpoints that didn't even exist, and as a result, we had a lot of failures, a lot of remote write request failures. These remote write request failures end up causing more network load, more CPU load, and if there hadn't been a hard limit of 20 replicas, it might have even caused our hashing to be scaled up even higher. Another issue that we spoke about earlier is that the hashing configuration loading can take a really long time and is non-deterministic, so some of the pods might load it before others. This means that we can have a split brain in our hash ring where some of the pods have the old hashing configuration and some of the pods have the new hashing configuration. The way that we chose to address this was to have a sidecar that automatically loads the new hashing configuration whenever the config map updates in the API. However, this has some other downsides to it. Namely, when all of the pods update the configuration at exactly the same time, there's an instant of time when none of the pods are available. This is because when the hashing configuration changes, the Thanos receiver takes itself offline temporarily when it flushes its TSDB. We flush the TSDB whenever the hashing configuration changes because we don't want data from one tenant to leak into the TSDB block of another tenant, because when the hashing configuration changes, we might also be changing the tenants that correspond to a pod. This downtime can take a lot of time, and it means that all 15 of our pods might be down at exactly the same time, and this could take a minute. And during this entire minute, we have no ingestion capability. So even though we have a replication factor of 3, for example, it doesn't really do us any good because all the pods are down. Another option we could have is to perform a rolling update of the configuration, where we only allow one pod at a time to update its hashing configuration. However, the downside of this is we have a longer amount of time where we have this kind of split brain effect, where some of the pods in the beginning have already updated the configuration and the pods at the end haven't. At the same time, whenever the pods are updating, they're still going to be getting traffic forwarded from the other pods in the hash ring. This is because the Thanos Receive Controller doesn't consider the readiness or unreadiness of a pod when it produces the endpoints array. Even though unready pods are taken out of the load balancing group for requests that are coming at a service IP, these pods can still get requests forwarded directly to them from pods in the hash ring. So when a pod is temporarily crash looping, or maybe it's temporarily offline because it's flushing its TSDB, the other pods in the hash ring are still going to be making gRPC requests to it and causing extra load on this pod and causing more trouble for this pod that's already struggling. One way that we can address this issue is by using backoff logic. And in fact, we actually already have a PR in the Thanos repo for implementing exactly this. Maybe by the time that you see this talk, it's already merged. A further improvement would maybe be for the Thanos Receive Controller to consider pod readiness when generating the endpoints array. Finally, one big issue that we have in Thanos Receive is the way that we forward requests in the hash ring. So normally remote write requests contain a lot of time series, and each time series hashes to a unique value that destines it to one node in the hash ring. When there's enough time series in the remote write request, statistically it's very likely that some time series will be destined for every node in the hash ring. So we might have one incoming request and it can result in 15 outgoing requests inside of the hash ring. Even though the Thanos receiver batches requests that are destined for the same node altogether, we still end up having a lot of traffic inside of the hash ring for one single request. This means that each incoming request is multiplied by the number of nodes in the hash ring, although each request is proportionally smaller, minus some gains that you would have had from compression. So the larger the hash ring, the more intra-hash ring traffic is generated for each request. Right now, we're in the process of investigating some different solutions for this, and we're specifically looking into having tiered layers of hash rings, kind of the same way that the Alert Manager project has tiered routing trees. So what's the deal with the Thanos receiver? Is it stable or is it not stable? Can we use the hash ring stuff? The answer is that yes, but it's complicated. As we saw earlier, when we have a stable sized hash ring, we can happily ingest all of the data that we send to it. But it's when we have a scaling event that we trigger some instability that leads to more instability. This means that using automated tools like the horizontal Pod Autoscaler can lead to unpredictable results. Yes, it'll probably stabilize at the end, but we're not exactly sure. We can partially mitigate some of these uncertainties by implementing policies, scaling policies in the horizontal Pod Autoscaler, which is something that's new in the V2 scaling API. Another thing we can do is we can start to work on a lot of the improvements that address the problems that we identified earlier. One of the things that we could do just off the bat is eliminate the need for downtime whenever a hash ring change occurs. As we mentioned earlier, whenever the hash ring is reconfigured, the Thanos Receive pods temporarily take themselves offline while they flush their TSDB. One thing we could do is essentially pivot to an alternative TSDB and keep ingesting data while we're flushing the old one. Yes, there's going to be some trade-offs where we have higher CPU and memory utilization, but a lot of the recent improvements that the Cortex folks have been making in Prometheus and TSDB have improved significantly the resource utilization that might even allow us to make these kind of trade-offs. Another thing that we could do would be to use consistent hashing. So one of the problems that we see when we have this split brain effect in our hash ring is that one group of pods that receives a request thinks that the time series contained in it should be forwarded to another set of pods with a different view of the hash ring. These pods, on the other hand, think that the time series should go to the first set of pods and they forward to each other infinitely. Using consistent hashing will allow us to partially mitigate this because we could reduce how much keys get redistributed when a new node is added to the hash ring. Alright, so that gives us a lot of ideas for ways that we can improve the Thanos project. So hopefully some of you feel inspired to contribute, and I hope to see you all on GitHub. Thanks a lot for watching. That's what I have for you today, and I'll stick around for questions.